bir şey yaptığım için o biraz garip. I was going to talk about the condition. I decided not to actually that. Let me work with this definition. The given an operator A has one literally or one image product space with transpose denoted as transpose into is defined by şöyle bu vektörün herhangi bir x'teki değeri x'ler okay, so A transpose is just another linear map so that at any x, its value is described by this relation, namely this vector in product with any vector is just equal to this gadget. Okay. Şöyle bir exercise var. İsterseniz onu yapalım. Okay. Evet. Aha. Evet. Transpose satisfies this. Let's see proof of this. Now, A hat, B hat, transpose applied to X and now Y is Y. It should be just X times A hat, B hat, Y, right? The definition of transpose is this. But you see, I can write this as follows, because you know this okay. Şöyle düşünün. This is just X times A times something. So that is just equal to A transpose x times b hat of y, right? Because a hat transpose times x times a vector is just x times a hat y. So if I just take y to be just b hat y, so just consider this thing as y, then a hat y is just a transpose x times y. Okay. But then I can just do this one more time. Right? Consider this thing as a single x. X times b hat y is just yani aslında belki şunu şöyle mi yapmak lazım? Daha şöyle. Hayır, tamam. Tamam. Okay, so just I can just take this gadget over here. So this is B transpose, A transpose, X, Y. Değil mi? Yani şuradaki operatörü buraya transpose oluyor. I just first get this over here and then we get over here. So we get this. So what we see is that this gadget inner product with y is the same thing as this gadget inner product with y, which is true for all y and b. Since this is a non-degenerate inner product, this implies, so this implies A hat B hat transpose of x is just B transpose A transpose of x, right? But this is true for all x, therefore A hat B hat transpose should be the same as B transpose A transpose. Okay. We have another proposition. If A is orthogonal, then this product is just identity transformation. Now, what is that? Proof. This is orthogonal means if it is orthogonal, then we know what A hat x, A hat y is the same as xy, right? For all xy in B. But then I have the following. Just take this A hat to this side. Then so the product of x and y, which is just A hat x, A hat y, and that is just equal to x times A hat transpose A hat y. And this is true for all y, right? For all y, or for all x. For all x. So inner product of x with y is the same as inner product of x with this gadget for all x. Therefore, this vector and this vector has to be same. Değil mi? Bütün vektörlerle iç çarpımı aynıysa iki vektörün, o iki vektör aynı olmak zorunda. So these are the same. In other words, A hat transpose A hat y is equal to y. And this is true also for all y. But this implies that A hat transpose A hat is just the identity operator. Yani ortogonal demek ortogonalse transpozuyla çarpımı kendisine eşit demek. Peki. Şöyle diyeyim. Okay. Let A hat be an orthogonal. Not orthogonal. Özür dilerim. Linear map. Linear operator, and let's say parameter En an orthogonal basis. For B, say the matrix representation of A hat in this basis, let's say beta is just Aij. Then here is the claim or proposition. The matrix representation of the transpose operator in the same basis is just the transpose of the matrix representation of A hat. So it's just A. Okay, let's say it is Bij, where Bij is just Ji. So this transposition is the same as the matrix transposition. Yani bir operatörün transpozu aslında onun ortogonal bir basis'te matrisini yazdığınızda o matrisin transpozunu almaktan farklı değil.
Hocam bununla ilgili örnek çözeceğiz mi?
Önce ispat edelim, sonra örnek çözmekten kastettiğin hani örnek yaparız. Şöyle diyeyim. Şimdi. Okay. Şimdi şey nedir? Head of değil mi? Bu ait kalımı değil mi? Ait kalım ne olacak? Bir J ait kalımı bunun J evet. That just the ith column. So 1 I, A, 2 I, A, and I. All right. Okay. Now, we know what? We know that a head of EI inner product with integer is just EI inner product with the transpose operator applied to integer, right? Now, what is this gadget? AEI is this thing. You take its inner product with EJ. Inner product of EJ with E1 is 0, with E2 is 0, and so on. Only this inner product will be 1, all others will be 0. So when I plug this into here, this thing will be just AJI. AJI. And the matrix representation of this a head, the matrix representation of this is just B, right? Bij. Therefore, this thing will be just what? I can write this like this. Similar to this one. So what will be this digit? This will be just the matrix element B. But what will be the entries? You see here I have I and J, but here we have J and I. Therefore, this should be B. These are switched, therefore these two will be switched. So IJ. Therefore, AIJ is just AJI is just EIJ, or AIJ is EJI. Therefore, these two matrices are just transposed of each other. Right? So this finishes the two. Come on. Bu da biraz şapkadan şey çıkartmak zorunda. Tamam bir ispat bitti. Okay. Şöyle. Üç, beş. Şimdi şuraya geçeceğim. Böyle geçeceğiz. Scalar product for complex vector spaces onu yaptık, değil mi? Hermitian inner product diye vermiştik. Şimdi isterseniz şeye başlayalım. operators. Okay, so I will consider either a real inner product space, and then for real inner product space, I will talk about symmetric operators, or about complex inner product or Hermitian product spaces, and then I will talk about Hermitian operators. So, if this is a inner product, then if V is a real inner product space, a symmetric operator heads from V to V is an operator so that any transpose is just A. In other words, its matrix representation in any orthonormal basis is a symmetric matrix, right? Its transposes to each other, to itself, right? That's why it's called symmetric, because its transpose is equal to itself, which means that if I choose an orthonormal basis for this inner product space, the matrix representation of a head is a symmetric matrix. If this is a complex vector space, with an permission here for that. Say the book and inner product ama burada zaten bir şekilde tarif etmedim. Ben daha transportta tarif etmedim. Şöyle, pardon, şunu farklı yapayım. Now, let's read complex vector space with an permission in it. So I have a permission in a product with complex values. Permission means just recall that it's something like this. So it is linear in the first component. So if I have, let's say, x1 plus lambda x2 y, this is just x1 y plus lambda x2 y, but it is conjugate linear in the second component, namely if I have, okay, we have this. These two are not equal as in case of linear, real linear product, but it is conjugate. And therefore, right, Hermitian has this property. Therefore, if you have, let's say, something like this, now this thing is equal to what? This is just, if I interchange these two, then I have y1 plus lambda y2 x, but then I need to take its conjugate, and that is equal to what? If you forget the conjugate, this is just y1, and then in the product with x plus lambda y2 is in the product with x, and I have conjugate here. This is a complex number, this is another complex number, and this is a complex number. So I have this arithmetic operations here, and then I take conjugate. This is just equal to the following: conjugate of this plus conjugate of this, and then conjugate of this complex number. Conjugate of this. But this is just x times y1, and then here I have number conjugate, and this is just x times y2. So what happens is that if it is Hermitian, then it is linear in the first component, but it is conjugate linear in the second component, meaning that constant scalar spheres goes out as conjugate. Okay, so it's not linear in the second component, it is conjugate linear. Like this constant goes out as number conjugate. So it is linear in the first component, but conjugate linear in the second component. Okay. All right, so we will say that okay. Am I correct? Or permission vector space. So it's a complex vector space with a Hermitian linear product. Okay, has permission. Transpose veya buna şey diyelim. Şöyle. Sabit. Şimdi ben şöyle notasyonu kullanayım. Define. Şöyle. Agent dagger x y is just x. So it's like transpose, but instead of an inner product, we have conjugate unconditional. Yani real'daki transpose operatörünü kompleks versiyonu. Aynı şekilde tarif ediyor ama bu bildiğimiz inner product değil, conditional. Böyle olursa in this case so similar to transpose of an operator if we orthogonal basis one değil. Şimdi şuna bakabiliriz. Bu nesnenin matris gösterimine bakabilirim. Bir de yani orijinal operatör matris gösterimine. Real'da neydi? Bu bunun doğrudan transpozuydu. Ama burada sadece transpose değil bir de conjugation işlemi olduğu için bu şey olacak. Önce transpozunu sonra da konjugasını alacağız. Veya tersine önce konjuge sonra transpoz. So this is just conjugate transpose or transpose conjugate. But we have another notation for that. Notation. For an operator, so or matrix transpozun konjugesini almak yerine doğrudan serisi sağlayacağız. Notation bu. Yani bir matrisin transpozunu alıp kompleks matris tabii ki sonra konjugesini almak işlemini sadece bu sağlayacağız. So we have what? We have Şimdi an operator on an Hermitian in product space is called Hermitian if a head is equal to its dagger. So this means what? You just in for matrices in terms of matrix representations, this will correspond to. So if this corresponds to a matrix, this will correspond to the in the same basis a star, right? Matrix representation. It means you take transpose of this matrix, and then you take conjugate of each element. Let's write down some examples of such operators.
Hocam en sonki kısmı bir daha anlatabilir misiniz?
Bir operatörün permission olması, yani bizim real in product space'lerde simetrik olmasına denk. Bir operatör transpozuna eşit olacak ama burada transpoz işlemi yok sadece, bir de conjugation işlemi var. Yani transpoz konjugasına eşit olacak. O da şu demek, herhangi bir orthonormal basis yazar alırsanız o basiste bunların matris gösterimleri, birisi A matrisi ise diğeri A star. Yani A star dediğimiz şeyleri A transpozunu alıp ondan sonra bir de konjugası veriyorsunuz.
Teşekkürler hocam.
Yılda sadece bu var ama komplekste bir de transpozu konjugeyi koymak. Mesela örnekler yapalım. İlk önce let's say B is and this is the standard in the product, so V, let's say just UI, and from 1 to n, standard in the product. In the product. Any matrix in any matrix defines a linear operator, and a symmetric or what? Symmetric operator means just a symmetric matrix. For example, given by this matrix, let's say 1, 2, 3, 2, 5, 4, 0. Right? This is a symmetric matrix. So this is a symmetric operator. Okay. If we choose, let's say, a complex vector space, let's say C, and in that case, our standard permutation in the product was this UI, but I'll take conjugate here. So in the second component, I take conjugate. So this is the standard permutation in the product, and permission operator, symmetric operator will be something like this. So let's say transpozunun konjugesi kendisine eşit olacak. Dolayısıyla diagonal mekanizmaların reel sayı olması lazım. Mesela şöyle diyeyim. 3 5i. So this will be just 3 plus 5. Let's say minus 1. And then here, let's say minus 4 plus 2i. So, okay. Here I will have minus 5i. Here I will have minus 4, minus 2i. And then let's say 0 here. Okay. So, this matrix is permission, namely, no, it's dagger, but if I just consider this as a matrix, this is just a head star, conjugate transpose. So it's equal to its conjugate transpose. Yani bu matrisin transpozunu alıp sonra da konjugesini alırsanız bunu elde edersiniz. Değil mi? Transpozuna eşit değil. Çünkü transpozunuzu aldığınızda 3 eksi i yerine 3 artı i geliyor. Eşit değil. Ama bir de konjugesini alırsanız eşit olacak. Right? All these entries are conjugates of each other. Tamam mı? Şimdi niye bunlar önemli? Şu yüzden you will see that if you have a Hermitian matrix or Hermitian operator,
Kamera kaldı hocam.
tamam. Or symmetric operator on a real vector space, then those operators are diagonalized. Okay, you will see that. When we function or symmetric operator. So this is on a complex vector space, in a product space. This is on a real inner product space. Any such operator is diagonalizable. And so if it is diagonalizable, then you have a basis of eigenvectors, right? Consisting of eigenvectors of that operator. Those eigenvectors can be chosen as an orthogonal basis. Okay? Diagonalizable, and the basis in which these operators are diagonal can be chosen to be orthogonal. Yani bazıları da ortonormal seçebiliriz. Tamam mı? O yüzden bunlar çok özel şeyler. Otomatikman mesela since this matrix is symmetric, I know that this is diagonalizable. Okay, this is also diagonalizable, and moreover, we will see that all eigenvalues of well, since this is diagonalizable, we expect that all the eigenvalues are real. Actually, it is not clear, right? I mean, the characteristic polynomial of this is the third degree polynomial, and for a third degree polynomial, the roots doesn't have to be real, right? Maybe some of the roots are complex numbers. But if it is the characteristic polynomial of a symmetric matrix, then it has only real roots. Okay, so the eigenvalues are real and the eigenvectors are orthogonal to each other. And the same thing here. If it is even a complex matrix, so the characteristic polynomial of this will be a polynomial with with complex coefficients, but actually it won't be a complex polynomial. It will be a real polynomial, but the thing is that the roots are real. Tamam mı? Yani şu polinomun bu matrisin karakteristik polinomunun bütün kökleri de reel sayı olacak. Değil mi? Bu müthiş bir şey. So that's the next thing we will do, but we will do it next week. Tamam mı?
Hocam ikinci için de basis normal bir basis değil mi?
Evet.
Teşekkürler.
Hı hı.
Hocam bir de çalışma kağıdı gönderecek misiniz bu hafta?
Ee,
İkinci midterm için.